This video is on the Nernst equation. So let's review our galvanic cell. So we've been doing galvanic cells that are starting out in their standard state. So this is our zinc copper cell that we've already done before. So we have 1 molar zinc nitrate in our anode compartment where oxidation occurs. And then we have 1 molar copper Roman numeral 2 nitrate in our cathode compartment where reduction occurs. So when the switch is up, we have our solutions. Then as soon as we close that switch, the cell starts operating and the zinc atoms come into solution as zinc ions, increasing the concentration of zinc ions. Our electrons travel through and the copper ions come up and plate onto the copper electrode, decreasing the concentration of the copper Roman numeral 2 ions. So as soon as our salt bridge, the salt bridge is there to maintain neutrality, as soon as our cell starts operating, our concentrations change and we are no longer in standard state. So now we're going to look at how do we calculate the E value when we're in non-standard state conditions. All right, so let's take a look. So we have our E0, which is standard state for all reactants and products. And we're going to use our delta G equation to be able to get an equation for the E value. So we already have seen that delta G equals delta G0 plus RT, the ln of Q. So now we're just going to substitute in because we know that delta G equals negative NFE. So negative N, Faraday's constant, E equals negative N, Faraday's constant E0, plus RT, the ln of Q. We want to get E0 by itself, so we're going to divide both sides by negative NF. And that gives us the E equals the E0 minus RT over NF, the ln of Q. This is the Nernst equation. Now, often our temperature is room temperature, which we take to be 25 degrees C or 298 Kelvin. And R is a constant, Faraday's constant is a constant. So at 25 degrees C, when we substitute those numbers in there, our equation becomes E equals E0 minus 0.0591 over N, the common log of Q. So these two are the same, except this is specifically for 25 degrees C. And for some reason, they changed the natural log to the common log. So you can do that by multiplying the natural log by 2.3. So this equation is often how you will see the Nernst equation. So now we can go through the mathematics that we've done before. What happens when our Q is less than 1? When our Q is a fraction. If Q is a fraction, the log term is negative, and the negative of a negative is positive. So our E is greater than the E0. If Q equals 1, when we're in standard state, the log of 1 is 0, and our E equals E0. And then if our Q is greater than 1, then this term is positive, so we're subtracting, so our E is less than our E0. And we can also derive this for when we are at equilibrium, so at equilibrium, our E is 0. Our battery is dead. It does not run. And at equilibrium, we know that our Q equals the K. So we can plug in for equilibrium. So we would have 0 equals the E0 minus 0.0591 over N, the common log of K. So this gives us that E0 equals 0.0591 over N, moles of electrons transferred, the log of K. So if we know our E0, we can calculate the K. So let's see how this works for a galvanic cell. So here we have a silver and nickel galvanic cell. And we have a nickel electrode in some 0.0010 molar, oops, I've got the molar nickel Roman numeral 2 nitrate. And then we have some silver in some 1.0 molar silver nitrate. So first we're going to identify which compartment is the anode compartment and which is the cathode compartment. So remember to do that, we check our reduction potential charts. And starting at the top, the first one that we hit, which is the silver ion has a greater reduction potential than the nickel ion, which is right here, all the way down here. So this means that the silver ions get reduced and the nickel metal, we have to flip this, gets oxidized. All right, so the silver gets reduced, so that means that this is our cathode compartment where we have our reduction, and then this is our anode compartment where we have the oxidation. So our half reactions for the reduction, we have Ag plus 1 electron, gives us Ag solid, that's aqueous, of course. And then for our oxidation, the nickel metal, the Ni solid goes to nickel ions, aqueous, plus 2 electrons. All right, I don't know if I've mentioned this before, but there is a notation, it's called line notation, to describe a cell. And so you start out with your anode, so Ni solid, put a bar, and then what it is oxidized to, the Ni2 plus, then double bars, kind of like, our salt bridge there, and then our Ag plus going to Ag. So this is the notation that describes that cell. All right, let's get back to our equation here. So now we can figure out the E0 for our cell. The E0 equals the E0 of the reduction plus the E0 of the oxidation. So the E0 of the reduction from our chart, silver 0.80 volts. And then the oxidation, we find nickel right here. So it's negative 0.25, but remember we're flipping this to get the oxidation half reaction. So we got to flip the sign. So it becomes positive 0.25 volts plus 0.25 volts. So now we have our E0, and that is 1.05 volts. So it's positive, and that means that it is spontaneous. Okay, so we want to calculate the E for the cell at these conditions, which are not standard state. So we need to be able to calculate our Q. So for that, we want to write the balanced chemical equation to figure out what the proper Q is. So we've got our Ni going to Ni2 plus 2 electrons, and Ag plus an electron going to Ag. So we need to have balanced electrons, so we got to multiply everything by 2. And then our electrons cancel out, and we end up with 2Ag plus aqueous plus Ni solid yields Ni2 plus aqueous plus 2Ag solid. So now we can write our expression for the Q. The Q is where we are, and Q always goes to the K. All right, so our Q is the product concentration. And remember, we don't have solids in the Q or the equilibrium expression. So our Q is the concentration of the Ni2 plus over, and again, that's not going to show in the equilibrium or the Q expression, over the concentration of Ag plus squared. Remember, for our equilibrium, we have to take into account the coefficients. All right, so our Q here then is our nickel concentration is 0.0010, and our silver is 1.0 squared. So our Q is 0.0010. So now that we have that, now we can calculate the E of the cell. So the E of the cell equals the E0, and we'll assume 25 degrees C, unless, we're told otherwise. So 0.0591 over the number of electrons transferred is 2 times the log of Q, which we calculated to be 0.0010. And then, so E equals our E0, we calculated that. Where's that? 1.05 volts minus, all right, so this is 10 to the negative 3. That's going to be a negative number, negative and negative. That term then will end up being positive. Okay, so 0.0591 divided by 2 times the natural log of 0.001. Okay, so this is a negative 0.089 volts. So our E is 1.14 volts. So the E, under this concentration, we have more battery life than under that concentration. All right, so that is how you use the Nernst equation when you have non-standard conditions.